Hi everyone, this is Brian Lane from the University of North Florida. I am excited to have recently received two grants, one from the VOYA Foundation, one from the American Institute of Physics, to support teacher professional development to integrate computation into high school physics and chemistry classrooms. We're very excited about this because computation has not really made a whole lot of headway into the high school context. We have a pretty good idea of how to do it at the undergraduate context, and we would like to share those insights with Florida high school science teachers. And we still have some spots left. On the VOYA grant, we are specifically using computation to integrate quantum topics into the high school context, but on the AIP grant, which is just now starting, we are looking to recruit physics teachers to integrate any physics topic using computation. So anything you would like to support through the use of computer programming, we can help you figure out how to do. This is a paid PD opportunity. We have a limited number of stipends available for teachers to participate in either program. And so what I'm sharing in this video is a presentation I recently gave about the quantum program at the Florida chapter of the American Association of Physics Teachers, and then the other program through AIP. It works very similarly, it just doesn't carry the quantum restriction in terms of the topic. That one is open to any topics that physics teachers want to incorporate computation using. So without further ado, here is my presentation. The link to that presentation slides are in the description below, which also includes a link to my university email so that you can contact me if you are interested in participating in this PD for Florida high school teachers. Good morning, everybody. Like Grace mentioned, I want to talk to you about some efforts we are making here in Jacksonville to help high school teachers integrate some quantum concepts into their high school classrooms. We usually don't think about quantum when it comes to high school, but I hope to convince you that we need to start thinking about it. I'm here on behalf of my collaborators, Dr. Terry Galante from our College of Education, and Abby Pruitt, our undergraduate research assistant. A little bit off here. Okay, we'll just do the best we can with it. I guess if I go like this, you can see the whole thing. Okay. I also want to acknowledge that this is supported by a grant from the VOYA Foundation that we are using primarily to financially stipend teachers who are participating. So what I want to do first is hopefully persuade you that we do need to start thinking about preparing high school students for a quantum infused future. Not that we want them all to be experts at solving the time-dependent Schrodinger equation, but just think about the familiarity you want them to have with force and energy now. That's the level of familiarity you want them to have with quantum concepts in the future. Then I want to motivate us to think about using the spins first approach to making this a little bit more easily accessible for our students, and then using computation to improve the accessibility even further. We'll talk about how we're structuring our professional development for teachers, and then what have we seen so far in our first couple months of implementation. So we're quickly approaching a point in our society's history where your average high school graduate is going to need some familiarity with quantum concepts. Again, not that we want them doing a bunch of quantum research or building quantum computers, but maybe we want them to be able to interact with a quantum computer, or maybe some of them go into a mechanics position to fix quantum computers, or maybe some of them go into a field that's even tangentially related to material science or using nanoscale devices. These are things that are going to be showing up in our everyday lives more and more over the next several decades. And so we would like students to have a background, again, kind of like the way we think about their background in forces and energy now. We don't expect them to be experts in it by any stretch, but we do want them to be conversant with it, familiar with the language, and know that how to tell the good research from the bad, right? And of course, this is challenging because quantum, it's got a whole lot of mathematical baggage to it, right? Thinking about the first page of Griffiths, where you have a partial differential equation with complex functions that you have to interpret in terms of probability, and that you need linear algebra to really treat. I mean, you need 4 junior, senior level math classes just to understand the first page, right? That's obviously not going to happen at a high school level, so we need to do something. But let's start early, because the other reason quantum is challenging is because of all the weird counterintuitive results we get. We have to start thinking about things as waves instead of particles. that the universe is fundamentally probabilistic instead of deterministic. That's a mind shift that takes time that we don't necessarily accomplish in a one semester senior undergraduate course. But how do we overcome the mathematical barriers while also making sure we present the quantum in all its weird glory, right? Well, we're taking kind of a twofold approach. One is we're using the spins first approach instead of the wave function first approach. And the second is we're using computation to help kind of put some of the math to the side so that students can focus on the sense making, right? And so what do we mean by spins first approach? Well, spins first came out of Oregon State's Paradigms in Physics program. The idea is that instead of starting with the esoteric, literally complex wave function, you start with spin 1/2. So wave functions present a lot of difficulties for students. For one, students see waves as complicated. I think, I haven't looked into this too much, but I get the sense that we tend to see waves as a structure that's got peaks and troughs, and you count the number of peaks and troughs. But students see it as a function that has all these different values that they need to keep track of, and it could be doing anything. They don't just see the patterns to it. There's also the fact that the wave function, I'm sorry, the students don't think it's a wave. It's not a sine or cosine. They don't think it's a wave. So that's a conceptual bridge that they have to get across. There's also the fact that we're talking about an infinite dimensional Hilbert space, right? We try to get them to think in 3 dimensions. Now let's go to infinite dimensions. That's conceptually challenging for our students. Also, the fact that your position has to go to plus and minus infinity, unless you're willing to live in the infinite square well your entire life, like that's challenging for them. They don't extrapolate to infinity as easily as we do. Also, how do we compare wave function theoretical results to experiments? I certainly don't have a lab that a high school class could do in an afternoon to confirm what the wave function is doing, right? And then, of course, there's all the mathematical baggage we mentioned earlier. On the other hand, if you start with spins, you can start with spin 1/2, start with electrons. It's up or down. It's a coin flip. Conceptually, that's very accessible for students. They understand a 50-50 probability, right? Then your psi, instead of being an infinite dimensional function, it's now a 2-dimensional column vector, which they understand how to use. They understand the concept of an up component and down component. They're already learning about that. Some of them even get to a little bit of matrices in their pre-calc class, I seem to remember having in mind. But we never learned what matrices were for, right? We were just a grid of numbers that you do some math with. This would actually give them a reason to be learning matrices. And then, of course, this is directly comparable with experiment. I can show students a video or simulation about a Stern-Gerlach experiment and see why we call it spin up and spin down, because they separate when they reach the screen at the end of the experiment. We think this comes with less mathematical baggage, or at least comes without any calculus, because I can map everything onto a 2D column vector. Is that still too much mathematical baggage? We don't know yet. That's part of what we're investigating. But importantly, this approach allows you to get to the quantum sooner. So instead of wading through pages and pages of defining ladder operators so you can get to the eigenstates of a harmonic oscillator, this gets you to the quantum stuff sooner. You can get to uncertainty principles sooner. You can get to expectation values, the variational standard deviation, that stuff sooner. And so then we're hoping to overcome the remaining mathematical baggage by using computation. So the stuff that's left that the students may not be familiar with is some matrix stuff and some complex numbers stuff. Because if we really want to do spin, we do need square root of -1 to get Sy. So by computation here, we mean using a computer to facilitate the study of a physics problem. We do not mean the students open a blank Python notebook and start writing. We mean that we hand them about 30-something lines of code. The goals of using computation here are to reduce the mathematical baggage, allow us to open up new problems for study. So beyond the context of quantum, using computation, I can do things like air resistance or free body gravitation that usually we have to skip in an intro class. And also getting past some of the tedious math. So even with all this 2x2 matrix stuff, there's still a lot of little calculations to do. If I can offload those to the computer, then the students' brain cycles can focus more on the sense making, which is what we really want, right? That's what we really want to have going on. And so in our context, this means using code that's usually about 30-something lines long to first create 2-dimensional spin states, spin up, spin down, right? 1, 0, 0, 1 in terms of column vectors, to make some 2x2 matrices and carry out the matrix math so that the students can focus on calculating the probabilities, the expectation, so something might be able to measure, so that ultimately they can treat this experience like an experiment, where they say, okay, I'm going to make a spin state that looks like this, is weighted this heavily in terms of spin down and this heavily in terms of spin up. What does that mean by expectation values? That's what we want them to think in terms of. And so this is what our professional development looks like. We are writing professional development modules in Jupyter Notebooks, which allows us to integrate the code with the documentation so that we can just go back and forth between, for example, the theory. Here we've got the spin matrices that look familiar to many of us, I'm sure. And then here we've got the Python code that implements those in just a few lines. And so then as a student, I can take this and say, I want to get the expectation value, so I'm going to do matrix multiplication, psi star, matrix psi, right? Our goal in these modules is to develop the teacher's content knowledge, because for many of them, it's been quite some time since they had a quantum class, if they had one at all. We present quantum applications. We're always linking out to articles on quantum memory storage, new experiments, things like that. But we also want to discuss the learning challenges that come with teaching quantum mechanics. What makes quantum uniquely challenging? And there's a lot of good research out there on this. Not a lot directed at the high school context. We're kind of hoping that research extends. We're going to note any differences that we come up with. So the teachers are expected to complete approximately one module per month. We'll talk about whether that's actually happening on the next slide. And then we have a monthly Zoom meeting where we will discuss this. Our next one is next Thursday. Looking forward to seeing Adam there. And at the end of the program, everybody who makes it to the end is going to get a stipend. That's the primary use of the VOYA funds that we've received. And then the facilitators were hosting weekly office hours just over Zoom so that people can complete this. So this is predominantly online. We're hoping we get to have like a reception or something at the end of the year, but we want this to be as accessible to people as possible. So thus far, we found that a few of our teachers really like the Jupyter environment. Some of our overachievers are already trying to use Jupyter Notebook beyond quantum. They're trying to do some stuff with geometry, projectiles, interfacing with their lab equipment, things like that. Our goal is to show how, is to explore how adaptable the quantum content is to the high school context. Particularly, we're interested in seeing that these math things we need to use of 2x2 matrices and complex numbers. What do we need to do to make those as accessible as possible to the high school students? Because obviously not all of them get to that in their math class, so they may be seeing it the first time here. Unfortunately, the biggest hurdle right now is that most of our teachers seem to be swamped by accommodating the continuing COVID pandemic. So we are located in Florida. We are supposed to pretend that COVID doesn't exist while also making all the accommodations as COVID continues. So basically our teachers are swamped. And so we are trying to be as accommodating as possible. We'll probably have a second cohort in the spring where we basically give folks a chance to restart, because there are some folks that have signed up, they've got their modules, we just haven't heard from them since then. So we're seeing some mixed results there. Speaking of which, we do still have some funds available for stipends, and we have a second grant that we got word of last month that is doing some computation in high school classes beyond quantum, so anything you want to do with that. And so we're looking to recruit for that cohort as well. So if you are at all interested, I've got a link there to a video series where you can actually see our modules that people are working through, and I've got my email in the link there as well. So thanks everybody so much, and I've also put the link to these slides in the program where you can grab the QR code there on the screen. Thank you.
Thank you, Brian. I guess we'll defer to the people online. If anyone has some questions for Brian that they'd like to ask, you can speak up now or put it in the chat. We'll see if you guys have any questions, and then people on campus will go to you next.
Okay. Looks like nothing in the chat yet.
Anybody on campus?
Take time to type. I've learned you have to wait longer.
Yeah, plenty of time. We will wait.
Thank you, Adam.
Brian, can you tell me about which, for the high school teachers who are involved in this, what kind of courses are they teaching, right? Is this, regular or honors physics in Florida? Is it just Florida teachers? Is it AP 1 or is it the calculus based? Who's getting interest? Who's showing interest so far?
Maybe let me talk about the geography first. So our initial target was Duval County, and we have kind of saturated the recruitment there. I don't think we're getting too many more out of Duval County. I mean, we're certainly welcome to. But fortunately, this is a much more flexible grant than, say, for example, NSF is, where if we couldn't get the teacher for NSF, we would have to beg and plead to go beyond. But we can go beyond. We're expanding it to Florida now. So I actually just sent a couple of emails out, kind of generally announcing this. We are recording this talk. So as soon as I get the video for this, I'll also send a copy of this video to the folks I've been emailing with, so they have a better idea of what we're doing. The classes, they seem to span all over. We're hearing from folks who are teaching standard physics. We're hearing from folks teaching AP. We're hearing folks not in public school system who are teaching, for example, physics of flight, which I think you're going to hear about shortly, that are just, they're interested in kind of putting this in wherever they can. Of course, one of the big constraints is where are they going to put this in the curriculum? And one of the biggest things we've heard from the AP folks is that after the AP exam, they pretty much get to do whatever they want, right? Because they're not prepping for the exam anymore. They're usually teaching seniors, so they're not getting them ready for the next semester. And so what we're hearing from a lot of folks who are teaching AP is that they would love to do this sequence in that month or so after the AP exam, which would be a really cool, capstone experience for the students. And so one of the things we do need to look at is if teachers are going to integrate quantum, what are the points where they can do that? Because obviously quantum is not part of NGSS or whatever standards people are working with. But if you're teaching energy, yeah, you can teach energy levels. If you're teaching lab skills, yeah, you can teach some probability. And so part of what we are doing, working with the teachers, is figuring out what the implementation looks like so that when we go and take this broader, hopefully with the next grant, we'll have a better idea of what that integration looks like.
Brian.
So one of your research questions there was whether this is actually going to reduce the mathematical baggage load or not. Did you have any ideas on how you wanted to frame the assessment of whether it actually did reduce the mathematical baggage?
Right. So one thing we're basically right now we are tracking work with the teachers. So this to go around, we are not worrying about assessing anything with students, because if we can get the teachers to even implement it at all, then that's a success. So part of what we're going to review at the end of this year is when teachers go to implement this, what do their lesson plans look like? So what did they feel like they needed to gloss over? What did they feel like they needed extra time on? If I take these, because these modules, in principle, a high school teacher could just take these modules they're working with, put them in front of their students, and the students could work through them. Now, of course, that's me as a university faculty saying that, so I'm not in that context. So part of what we can look at is the differences between our original template and how the teachers adapt it. And that is where my colleague over in education is invaluable, because that is right up her alley. So I generate the content and she decides the assessment, and it's wonderful.
Any other questions from anybody online or in the room?
So I know this is designed for high school teachers, but I know that there are some high schools where students do like honors projects.
Yeah.
Do you think this is something that an honors, high school student who's already done, their AP physics as a junior, we have these, I don't because I teach at college, but I get contacted occasionally by some of these high school students who are looking for an honors project, and they're often asking, can I do something in quantum? And I'm like, I don't know what to tell you because of the mathematical front loading. Is this something that a highly motivated high school student could run through?
I think so. Like I said, the two main mathematical things we're using is matrices and complex numbers.
Right.
I know that is accessible to at least some high school students. Elmarie is saying science fair project. Yes, as a science fair judge, I would love to see somebody do this for a science fair project, because you don't see a lot of computational modeling at the science fair. Another thing I should mention, we've also opened this up to chemistry teachers, because chemistry folks are already teaching quantum. They're already teaching energy levels. They're already teaching orbitals. And so this is a way to get a little bit more formalism into that beyond just showing the diagrams. I think you could also probably extend this to a highly motivated math student who maybe learns complex numbers and matrices in their pre-calc class, but says, I don't know what this is for. Well, a math teacher could also grab this material and come at it from the angle of, here is an application of the mathematical tools I've been teaching you, and then we kind of get the content in that way.
And then I have one follow-up question, and that is, are you familiar with the ACE Physics project, which is the tutorials based on the Spins First lab? It's out of CU Boulder, and a couple of other schools have.
I know I have heard that. Is that where they're doing the simulated Stern-Gerlach experiments?
Yeah, they built tutorials for it, but they have these cute, like, you have quantum mice and they have big eyes and small eyes, and you're in a superposition state of big eye and small eyes. It's pretty cute.
Okay, I have not seen anything with mice. So
okay, so I'll send you that link offline.
Okay, please, thank you. Yeah, because we do have them before they get into the Python. We do have them doing McIntyre's spin labs that we just provide them with that section of the textbook, because all that is change this piece of the sim and count the percentages and the collectors. There's no math involved beyond, do you know that probabilities need to add up to 100%. And so that's a good way to kind of get them conceptually going. And their goal at the end of the spin modules that we have in Python is to get the Python results to match those experiments when they do separated a spin in the Z, then separate spin in the X, and separate spin in the Z again. Oh, look, I got spin up and down again, even though I had spin up back at the beginning. Okay, perfect. And there is a link. I'm going to go open that. All right. Perfect. Thank you for that, Anne.
Yeah, I just wanted to add to, I can't quite tell her name. She was asking about how this would kind of be implemented in further areas other than quantum. And I was just kind of, I guess, bring up the topic of what we were discussing with the IB curriculum, how they use their IAs. And so even science fair projects and things like that, I found that going through all this, I could see definite, benefits from using this, because they're really curious or really ambitious for the students to actually use the computational skills to develop those models and things like that. So the science fair projects.
If I can get on the soapbox for just a second, one thing I heard somebody say on the Physics Alive podcast recently was that project-based learning really is the future of physics education, because there is no way in a 15-week university semester or 180 days of high school instruction, I can address every possible topic and every possible application that's of interest to every student, because they're all going in different directions. They all need physics, but they all need it for different reasons. And so if I can direct each student or a clump of students to go pursue a project that's in line with their interests, I know they're all going to learn the physics that they need. But that's something we collectively have not figured out how to do yet. And so but I think computation is a great way to do that, because it relieves those mathematical barriers, and you can go study any problem you want.
And they can make the plots and everything.
Exactly. And then they get the visualization, they come back and share, oh, look, we all use conservation of energy. That must be a big deal, right?